otherwise, you can see our agenda is pretty brief today. I have a little bit more math to show you, which wraps up the math that we're going to be doing for the next few class periods. And then we have our lab for probably the last half an hour of class, and quite frankly, it's not a half an hour lab, so it gives you a little time to work on the lab then as well to wrap things up. So again, we did our warm-up. All right, so on the top of your page 2, you have the same kind of table with equations and constants as I have on my screen on the right-hand side right now. What we have to go over today with our thermal math notes is we are going to be calculating the amount of energy to go through several different changes on this heating curve that was on your warm-up today that we looked at first semester. Quick reminder about the heating curve. You can see on my slides here, this first slope is when it's a solid state of matter. This first plateau is when it's melting if we're going left to right, or freezing if we're going the opposite direction. That occurs at the melting point of the substance. This second slope is the liquid state of matter. And again, it stops at the boiling point when we vaporize. So that's your heat of vaporization. And then finally, the last slope is the gas state of matter. What you can see on the top of your sheet of paper, where it says Q equals MC delta T, the C value, the specific heat capacity, again, how well matter can absorb energy before its temperature changes, that value varies based upon state of matter. That's why we have the C value for ice, the C value for liquid water, and the C value for steam listed there. Depending upon water's state of matter, it plays a role in how well it can absorb heat before its temperature changes. On the right-hand side, you see Q equals M times H. This is an equation that we used a little bit at the very end of last semester as well. And what you'll notice there is that there's a different amount of energy to melt something versus vaporize something. Vaporizing always requires more energy than melting, because when you melt, you go from a solid, where things are kind of held in place but just vibrating, and when you melt, you become a liquid. You're still attracted, but now there's kind of a flow. But when you go from a liquid to a gas, you break all attractions, and now things are just flying all over the place. Melting is loosening up. Vaporizing is completely getting rid of those attractions. So because of that, for anything, its heat of vaporization is always going to be higher than its heat of fusion. But again, our goal today is going to be focused a little bit more on the mathematics of this. So, here's the first sample question that you have in your notes that we're going to go over. It says, calculate how much energy would be needed to heat 12 grams of water from negative 10 degrees Celsius to 110 degrees Celsius. On the right-hand side of your sheet, on the right-hand side of your sheet, there is a spot for you to have kind of a heating cooling curve. So I'm just going to draw one right here. One of the things that we suggest students do is kind of map out the problem. And here's what I mean by that. Remember that this first plateau is at 0 degrees Celsius, and that second one's at 100. This question starts you off at negative 10 degrees Celsius, which is right down here. So this is negative 10. And it ends you at 110. The reason why we have that little spot for you to kind of graph this out, I hope you can see that it is not a straight line that's connecting these 2 points. Instead, we have one line right here. We have a second line right here. We have a third line here. We have a fourth line here. And we have a fifth line there. That means in order to solve this problem, we have to do multiple steps. The number one issue that students have with this type of calculation I'm about to show you is they try to do it in one step. They try to do Q equals MC delta T. My change in temperature is going to be 120 degrees Celsius. I'm just going to pick water C value and then I'm done. But it doesn't address actually what's happening. Because depending upon if you're a solid or a gas or a liquid, you absorb different amounts of heat. Heck, it doesn't address the fact that you have phase changes that occur as well. So, lesson. Hopefully you have a fair amount of room on your sheet of paper because this is going to take us a little time. Step number one. I am going to go where I have on my graph number one, where my temperature starts at negative 10 degrees, and I'm going to go up to 0 degrees. So in other words, I'm going to take my ice, because this question starts with ice. Oh, am I looking at the wrong one? Sorry. Here we go. This question starts with ice and negative 10 degrees. Let me redraw this a little bit too now, sorry. Starts at ice at negative 10 degrees. I'm going to get that up to 0 degrees. Okay? The mass in the problem is 12.0 grams. The heat capacity, the C value, you need to use ice's number. That's 2.03. Change in temperature. Final, which is 0, minus initial, which is a negative 10, gets me 10 degrees Celsius for my delta T. If I multiply that all out, and it looks like 3 sig digs, 3 sig digs, 3 sig digs, my first part, I get 243 joules. If I have ice at negative 10 degrees Celsius, it takes 243 joules to heat it up to 0. Are we okay with step one? Awesome. Step two is going from 0 degrees Celsius as ice to 0 degrees Celsius as liquid water. Now, if we're going on a plateau, the temperature doesn't change during that phase change. Any added energy isn't increasing its temperature, it's breaking apart its solid structure instead. So that's why in step number 2, the equation I'm using is M times H. The mass times the heat of, depending upon where we're at, this time it's going to be the heat of fusion. The mass was still 12.0 grams. Heat of fusion of water, if I look at my table, is 334 joules per gram. I'm going to hold 3 sig digs again. I'll give you 4,010 joules. Get this up a little bit higher for you. By the way, all of these constants that are on your note sheet would be given to you for a quiz or a test. I mean, we're not going to have you memorize these things. That's ridiculous. Okay. Step 1, take my ice at negative 10, bring it up to 0. Step 2, take my ice at 0, make it liquid water at 0. Step 3, I'm going to heat up my water now. And that goes up to 100 degrees Celsius, the boiling point of water. And hopefully you're starting to see why we gave you a whole bunch of space to do this problem.
How did you get that up?
Well, I guess it depends on how big you're right. That's true. Maybe it will be enough, maybe it won't be. Do what you can with it. All right, so 12.0 grams is still the mass. Now I'm going to use the C value of liquid water. Delta T, the final temperature I'm raising it to is 100. Minus 0, so change the temperature to 100. MC delta T. Whenever you are on a slope on that heating curve, you use Q equals MC delta T because the temperature is changing. Whenever you're on a plateau, the flat line across, that's when you would instead use mass times the heat of fusion or heat of vaporization. I get 5,020. For this one. We're over halfway done. I'm going to go back to my heating curve again. Currently, I'm at the red dot. I'm at liquid at 100 degrees Celsius. Normal conditions of pressure, that's as high of a temperature that liquid water can obtain. If I keep on adding heat, I am going to vaporize it. I'm going to turn it into a gas. So my fourth step M times H. But this time, I'm using the heat of vaporization. So my mass is 12.0 grams, and I'm going to multiply by that heat of vaporization, which is 2,263. This is going to give me a big number. 3 sig digs, 27,200 is what I see here. Give me a second to catch up with that, and then we're going to go back to my map again for the last step. My blue dot on the right is currently at 100 degrees Celsius for gaseous or steam for the water. The question wanted me to go up to 110. So I have one last little step. I have to heat up my gas. The mass of the water is 12 grams. The C value for steam, again on the top of your page, 1.99. I just right away wrote down the change in temperature. We ended at 110, we started at 100. Sorry if you wanted me to write that out a little bit longer. All right, that means Q for this step would equal 3 sig digs, 239. Yeah. What we just did was showed, because we started here, we have to take each line separately. 5 separate lines, 5 separate calculations. You got to add them all up now. So if you add all of this up, I kind of call this like Q total. You first add it all up, it's 36,700 joules. oh, sorry, 36,712 is what your calculator would first say. Let's start with that. If you are not a big fan of sig digs and don't care if you lose a quarter of a point because this was enough for you, you feel free to turn off your brain for the next 30 seconds. But if you want to know the rules for rounding for sig digs, when you add all these numbers up, this number went to the ones place for its 3 digits. This number went to the tens place. This number went to the tens place. This number's last significant digit was the hundreds place. This one was the ones place. The last digit of significance that they all had in common was the hundreds place. So 36,700 joules is what we call this final answer. And it popped up on you a little bit when we did delta T on the last Schoology. Probably the good news for you is because we're doing a lab today, there's no homework on this, so there's no getting frustrated over sig digs when you type in your final answer. Eventually, when we have a quiz, you will have a problem kind of like this on your quiz. Our plan is every warm-up that we're going to be doing the next couple of days to include a problem like this. That way, if you have questions about how to do the rounding, let us know. All we have left then, let me erase this, is one more question on your notes. And that's going to be our notes for today. I want to do a question that goes in the opposite direction. Because notice this one says you are cooled from 47 down to negative 18. So let's go the opposite direction for one problem to kind of wrap up our notes for today. And I'm going to start off by just mapping out my problem. And here, if I'm at 47 degrees, that's right around there. That's in the middle of the water. Negative 18, let's say it's right there. Remember, this is 0. And we're going to cool it this time. We're going to go to the left. Here's the good news about this problem. And again, we just, as a chem team, met the other day. We looked at the quiz that you're going to take in about, I don't know, a week and a half. This is less steps than the previous problem. I have one step to cool my water. I have one step to freeze my water. I have one step to cool my ice. 3 steps total. More commonly, that's what we're going to give you on an assessment. Because 5 steps, as you probably just seen on your own sheet of paper, I mean, Olivia, you write pretty neatly, and you had barely any space to spare there. We don't need to test you in 5 steps to know, do you understand that there's multiple steps in it. 3 steps does the job just as well. All right, so let's do this problem. Step number 1, I'm going to go from 47 degrees down to 0. The mass in this problem is 50.0 grams. The C value of liquid water is 4.184. And here's where we have to start to be careful. Delta T is final minus initial. Our initial is 47. We're going down to 0. 0 minus 47. Which means this is a negative 47. Which means when I solve for Q for this first step, it's going to give me a negative value. Negative 9,830 is what I have here. Now, does yours have 47.0 on your sheet? Oh, there's 47. So really, I should be going negative 9,800, shouldn't I? my step one. Sorry for that weird looking J. Step two. My water's at 0. I now need to get it to ice at 0. I need to freeze it. Remember, anytime it's a plateau, it's M times H. 50.0 grams. The next thing we have to be careful with. When you look at the heat of fusion on the top of your page, it gives you a positive 334 joules per gram. Because if you add heat, you can melt something. We're not looking to melt, we're looking to freeze. So what you need to do is put a negative sign in front of that in order to get to the right answer for that second part. So what makes this problem trickier, even though it's going to be less steps, is the negative part of it. 3 sig digs holds here, negative 16,700 is what my key says. My final step is going from ice at 0 degrees Celsius down to ice at negative 18. So back to MC delta T. And again, my delta T is going to be a negative value. Notice that each step, the delta T is negative, or the heat of fusion here is negative. Negative 1800 if I go to 2 sig digs here. Notice how my first step went to the hundredths place for sig digs, the second step went to the hundredths place, the third step went to the hundredths place. This one's going to be pretty easy for sig digs then. And again, correct me if I'm wrong, but I see negative 28,000. Was it 300? Yeah. Mm-hmm. Our lesson today was one more step of math that we need you to be aware of. Because when you're changing states of matter, you have to account for the phase changes, that's the plateaus that you see on the graph, and the fact that each state of matter has its own heat capacity, its own ability to absorb energy before its temperature changes. We have to be able to account for that mathematically. Now again, I said before, the lab isn't going to take all class period, and I think it would be useful to give you a little bit of time to practice this. So if we are at 8:55 right now, I would say 10 to 15 minutes of work time. That gives us plenty of time to come back together, explain the lab, do the lab, and still get done early today for those of you who would want to either do more practice problems or look at the lab or just kind of take it easy for the last bit of class. So you can do this on your own, you can do this with others at the lab bench or wherever you want to go. Let's give you about 10 to 15 minutes of work time. Okay? You turn to the back of your packet, it should have the heat capacity of iron lab. So let's all look at that for a minute here. If I read the very top, it says you'll be experimentally determining the heat capacity of iron. To do this, you will need to place an iron washer in boiling water for approximately 3 minutes. Next, quickly transfer the washer into 100 milliliters of water in a calorimeter and record the highest temperature reached by the water. Make sure to collect the mass and temperature data at the appropriate times. You can temporarily record your data below. Okay. Didn't give you an awful lot there. At the same time, today, you're going to be doing a lab that you have to turn in more of a formal lab report that you did once for Unit 2, once for Unit 3. You're doing it once for Unit 4. At the lab bench, I already have the water bath set up. Here it is. Don't be thrown off by the fact that I have a rubber stopper sitting in it. The entire point for the rubber stopper is you're going to take 2 metal rings today, find their mass, and then you need to heat them up in boiling water. What you can use is a crucible tongs. You grab it, you set it in, you grab it, you set it in. The reason for the rubber stopper is without it in there, the rings would sit flat on the bottom of the beaker, and year after year, when that's boiling, it's hard for students to grab the rings back out. But now they're kind of propped up by that, it's easy to take it out. So, first off, you will need a Bunsen burner. You'll hook that up, you'll light it, you're going to get this water to boil. While that's being heated up, you're going to want to find the mass of your 2 rings. And hopefully they're dry, so I'll dry off these for if anyone's over here. Then, it mentions calorimeter. You need to come over here and get your styrofoam cup calorimeter. You're going to need to come over here and get a thermometer as well. Because the directions state you need roughly 100 milliliters of water in your calorimeter. Remember, we need the mass of that water as well. We need the initial temperature of that water as well. So, if I were a student, I would, after I get my goggles on, we don't need apron today because there's no chemical, but we've got flame and we've got boiling water, goggles on. I'd get that started. I would get the mass of my rings. I would get my water in my cup and get the mass of that and the initial temperature. Once these rings have been in boiling water for about 3 minutes, what do you think their initial temperature is? If they were in boiling water. They're in boiling water. What's the temperature of boiling water? 100. So we're going to have rings that are 100 degrees Celsius. We're going to put it in our cup, again, using your crucible tongs. And then you're just going to mix. Kind of like when you mix the solute, but now you're mixing to allow the heat to disperse throughout the water. The metal's going to cool down, the water's going to heat up, and at some point they reach kind of thermal equilibrium, where they're at a certain final temperature. That's your final temperature to record. So the space that we provide in the lab pack is for you to write down those different measurements that you need to collect. Because if we don't collect the right measurements, we can't write the report very well. Now let's speak of the report a little bit. It says on the bottom half of your sheet, type a report to include a purpose, materials, a procedure, data observations, calculations, and a conclusion paragraph. Here's an example of a lab report that an AP Chemistry student did. Here's their purpose. I can make this a little bit bigger for you, although you don't have to really read the entire purpose. It's a 1 to 2 sentence statement of what they're trying to find and how they'll do it. I'll give you a hint. Look at the title of your lab. It helps to identify what you're trying to find. Then it's just a list of the materials that they used. Especially include things that measure. Heck, this was a calorimetry lab, so thermometer and calorimeter is there for that person as well. Then they give a step-by-step procedure. Step 1, what did I do? Step 2, what did I do? So not a paragraph format, a step-by-step procedure. Here's all of his data that he collected. Here's the mass of the calorimeter, starting temperature, ending temperature. We're going to be doing something similar here today. then he just wrote his calculations on the sheet of paper. So he kind of like hit enter a whole bunch to leave himself some space. But heck, he's doing Q equals MC delta T on here for part of this lab as well. Even though this lab has a little bit more to it, so we can ignore some of this other stuff. Okay, you don't have to do limiting reagent math and stuff like that. And then I'm going to tell you right now, this paragraph is way too long for you guys. You guys need one solid paragraph and that's it. The AP lab report needed a little bit more to it. I get it. So what you're going to be doing is, again, with a partner, and today let's just have the person that's right next to you going across. Now, Davey, you have no one next to you, but neither does Levi, so then you two are together. Again, we'll switch lab partners for the next lab that we do after that. With your partner, you're going to get goggles on. Again, what you need is to mask the rings, to mask the water, the initial temperature of the water. Get the water in your bath boiling so we can heat up the metal. And then eventually it's hot metal into the calorimeter. And by the way, once you do that and turn off your Bunsen burner, feel free to take off your goggles. And then we're looking for that final temperature. You've got about 27 minutes to accomplish this lab. Should be plenty of time. Go ahead, get your partner, get to a lab bench that has a water bath, and get started.